Hi, we are Warren Shepard and Sair Shaikh, and our paper is Progress Measures for Grokking via Mechanistic Interpretability. So some background and terminology. This paper concerns itself with phase changes, which are these points where the model performance or learned representation shift dramatically. Specifically, we are looking at the phenomena observed called grokking, which is where models abruptly transition to generalizing after a large number of training steps, seemingly very abruptly. So this paper comes in from the subfield of AI called mechanistic interpretability, which is a subfield focused on understanding the internal workings of small ML models by reverse engineering algorithmically what they're doing. And it is trying to come up with progress measures for things like grokking, which are like task-specific metrics that are more causally linked to the phase transitions and vary more smoothly and can show us what's happening beyond just the abrupt changes we see. The key idea here is that progress measures can be discovered via mechanistic interpretability and they can explain grokking. So the relation to our class and generative AI here is that large generative models use transformers, which are often considered like these massive black boxes with millions and billions of parameters. And since they have millions and billions of parameters, we have a very limited understanding of their internal workings. So uncovering how the internal workings of these transformers work, especially in these small cases, can explain how transformers actually use all the components they have, which is important for trust, reliability, and safety. And progress measures contribute to this goal. So the case study we have is modular arithmetic, which is you're given two integers, a and b, and you need to compute their sum, mod p. And the representation that the model ends up learning in our paper is this representation, which first starts with embedding, where the vectors a and b are one hot encoded into these Fourier components of sines and cosines at different frequencies, where there's some key frequencies that are highlighted at great strengths, which are multiples of 2 pi over p, where p is the where p is the modulo that we're taking modular arithmetic with. It then uses the attention mechanism to learn the sine and cosine identity we know from middle school, where it calculates the sine and cosine at various frequencies of a plus b, essentially mapping addition, modular addition to a circle. And in the MLP layer and in the unembedding layer, it essentially translates these logits to cosine of a plus b minus c at various frequencies. And the point here is for each logit c, this value is maximized if c equals a plus b. Therefore, it ends up giving the highest probability to the logit c if a plus b is c mod p. There's a lot of evidence that they found for this proposed algorithm. Specifically, network weights and activations exhibit a very periodic nature corresponding to these key frequencies. Moreover, as we saw in the previous slide, the unembedding matrix is essentially does a sum of sines and cosines to calculate what it's trying to calculate, and we see that it's well approximated by a sum of cosine and sines, especially at those key frequencies. Similarly, attention head and MLP neurons, we saw calculate this sum like sine of a plus b, and they're well approximated by degree 2 functions of sines and cosines, which correspond to the identity from middle school that we all are familiar with. Lastly, they also tried removing certain key frequencies from their internal representation and saw that that reduces the performance to random chance, meaning that those are the most valuable. And they tried ablating other frequencies and saw that that increases performance. They introduced two progress measures. Firstly, restricted loss, which is basically like loss, but only using the key frequencies and eliminating everything else. And excluded loss, which excludes key frequencies and leaves everything else. And they saw that the training mechanism can be divided into three phases: memorization, where the train loss decreases; circuit formation, where the train loss remains low, but the test loss remains high; and then cleanup, where all the bad representation is cleaned up and we see crocking. These correspond more directly to the progress measures that we defined. So essentially, there's two contributions that this paper makes. Firstly, to reverse engineer the algorithm transformers implement for modular addition. Secondly, it defines task-specific progress measures that correspond more typically with the task at hand. And this helps our understanding of how transformers use various components of their architecture, such as the latent space, the attention mechanism, and the MLP head to do the task that we want them to do. Thank you.